Okay, so welcome back to this course on logic. And can everybody hear me? Would you say yes? Oh, okay, good. Yeah, thank you very much. So we are in the middle of, we're gonna continue our discussion on the Herbal Theorem and how, so I'll give also some words on how this theorem can be used to come up with some algorithms for answering questions about first-order logic formulas. Okay, actually, not an algorithm, but semi-algorithm. So how it's related to automatic theorem proving. So something that we talked about last time is a Herbal structure. And okay. So we talked about Herbal structure. And then this is a reminder of Herbal structure. So the big picture is that we are given a formula F in first-order logic. And typically, we are interested in showing unsatisfiability of the formula. So that's the context where we're going to use this Herbal structure and the Herbal theorem and so on. So we are interested in showing this formula is unset, and we want to do it in a semi-automatic way. But so this is a general first-order logic formula. But this general first-order logic formula is quite complicated. So we're going to transform this formula in polynomial time to another formula f prime, which is equisatisfiable. So it's a satisfiability preserving transformation, but f prime is going to be in the Scholen form. So which means that f prime will have always of the form, bunch of universal quantifications, and followed by, sometimes we call it matrix, which is the quantified free formula f means which I wrote it as f prime star. But still, doing some reasoning about showing this f prime is unset is not going to be quite easy, because we have to think about really large amount of structure to check. And when this unset really means no structure satisfies f prime. So we have to think about really a lot of structures. But then we're going to study Herbal theorem, and we're going to prove it today. So this Herbal theorem say, instead of checking onset, instead of checking all those possible structures, it is okay to consider only some small subset of these structures, which are called Herbal structure. So if the formula f prime is unsatisfiable, which means that none of the structures satisfy the formula f, precisely when this formula f is not satisfied by any Herbal structures. Okay, so this theorem gives some form of optimization. Instead of checking f prime is not true for every structure, it's sufficient to just check this f prime is not satisfiable by a Herbal structure. So we're gonna use a Herbal theorem to simplify this, and then we will later use a Compactness theorem in propositional logic to come up with some strategy for showing unsatisfiability with respect to Herbal structure using resolution theorem proving. So we're gonna go to these steps that I just draw. So today's goal is to show how this step works. So here's a reminder about how the notion of Herbal structure. The Herbal structure, given a signature sigma, Herbal structure is a structure where many things are fixed. The underlying universe is fixed. Also, the interpretation of a constant is fixed. Interpretation of function symbol is fixed. Okay. What's not fixed is interpretation of a predicate symbol. So that's not fixed, but all the rest is fixed. Universe is fixed to be the set of ground terms over sigma, which means that any term which doesn't contain any free variables, that's going to be typically infinite, sometimes finite, but it's typically infinite. So but that's a single set which is determined by signature sigma. That's going to be the underlying universe of all the Herbrand structure of over sigma. Okay. Interpretation of a constant is going to be interpreted as itself because the universe contains the constant symbol, and constant symbol is going to be interpreted as this itself in the universe. Function symbol will be interpreted as a map that takes terms T1 up to Tn and just put symbol f in front. Okay, so it takes T1 up to Tn that leaves those are the elements in the universe, and the behavior of interpretation of f is just construct a new term which puts f in front of all T1 and Tn, and then in the application form. Okay, so that's the Herbrand structure. So it's much simpler because many things are fixed. And then we talk about the two theorems, which are, in the Herbrand structure, the interpretation of a ground term is equal to itself. That's because constant is interpreted as a constant. Function symbol is interpreted as just adding the function symbol. So for the ground term is concerned, it's just interpretation acts as an identity function. Translation lemma, we learn about translation lemma, but in the Herbrand structure, translation lemma is a bit much simpler. And then we say that Herbrand structure satisfies f where x is replaced by ground term t, precisely when f is true under this new Herbrand structure h, where x is now bounded to t. Okay, so I made a wrong statement a little bit. Herbrand structure, two things are not fixed. One is interpretation of predicate symbol. The other is the semantics of all the variables. So here we are changing the semantics of all the variable x here. Okay. So these are the two theorems we talked about, but the main result in this lecture is the one proved by Herbrand. And this is the Herbrand theorem, which say that if we have a formula in Scholen form, then formula f is satisfiable precisely when the formula f has a Herbrand model. Okay, and I express this Herbrand theorem in an unsatisfiable format. So because if you take a so-called contrapositive, 대우 in Korean, then this theorem is equivalent to say f is unset if and only if the f doesn't have a Herbrand model. Okay. So that's exactly the same statement as this Herbrand theorem. So that's what I mentioned before, but you can view it in this way. Okay, the theorem say f is satisfiable, then it should have a Herbrand model. And if f, now one direction of this theorem is quite easy. The easy direction is if f has an Herbrand model, so then it should be satisfiable. So this is an easy direction. That's because the satisfiability just means that it has at least one model, so that at least one structure satisfies f. But this direction say actually there is a very special kind of structure that satisfies f, which is there is a Herbrand model satisfies f. So then f should be satisfiable. So this is just coming from the definition of satisfiability. But the other direction is not obvious. Okay, so this is a non-obvious direction. So our task today is to prove this theorem. So that's actually an exercise I want you to do. But then here's a bunch of hints for the exercise. So the first hint is that now the one complication that comes from is the formula f may contain free variables. So not all the variables in formula f may be bound by universal quantification. But it turns out it's okay to consider only closed formulas. And the reason is, I'm not going to give a proof about this, but here's roughly the reasons. The reason is that if you have a formula, something like for x and for y, and then say you have a p, x, y, z. Okay, suppose this very simple formula, which doesn't say very much, but this formula contains free variable z. So then the satisfiability of this formula is, in a sense, there has to be some translation, in a sense, almost to say the same thing as satisfiability of this modified formula, where z is replaced by constant symbol. So the original formula case, maybe the signature for this formula maybe has a constant d and function symbol f and predicate p. But now in this new case, we now have a one more constant symbol c, d, and f and p. So these are comparing satisfiability across two different signatures. But it turns out it's quite easy to show if the left-hand side is satisfiable precisely when the right-hand side is satisfiable. And what we obtain by right-hand side we obtain the right-hand side by replacing all the free variable by fresh constant symbol C1 up to Cn. It's a bit like it's essentially an instantiation of scolomization, but if that make you confused, this is a kind of fact that, that allows us to focus on closed formula F only. Okay, so that's a hint one. The second hint is the non-trivial direction is this direction, which is the only if direction. And then here's a bunch of hints to how to do this, okay? To show the non-trivial only if direction, we can assume that because f is in that case is satisfiable, we can assume there is just some structure A which satisfies f. Okay? If A is a Herbrand model, great, we are done. But in general, A is not a Herbrand model. So now our task is to construct Herbrand model H from A. Okay, so that's what we have to do. And here as I said, in the Herbrand model, almost everything is fixed except the interpretation of predicates and interpretation of variables. Okay, so interpretation predicate and interpretation of variables are not fixed, but because formula F doesn't have any free variable, interpretation of a variable doesn't really matter. Whatever you do, it won't hurt. Okay, the only thing that matters is interpretation of each predicate symbol. And then for the interpretation of each predicate symbol, we are using this is specific. We do it in the specific way that's described in the slide. So this is the interpretation of predicate symbol. We have to decide when closed ground term, no, not closed, ground term T1 up to Tk belongs to the semantics of predicate symbol P under this Herbrand structure H. And then this, my hint say that actually if you do it in the way it's written in the slide, that works. And the way they say that, just look at this A, which we are given in the beginning. What A say? Okay, if A says the P, this A says there's a P T1 up to Tk has to be true. So then we said that T1 up to Tk is gonna be related by this predicate interpretation of predicate symbol P. Otherwise, we said this is not related by this predicate symbol P. Okay, so that's, in a sense, we are deriving the semantics of predicate symbols using this satisfying structure A. If you do it, then you can actually show that the Herbrand model that we just constructed is the one that we are looking for. And then what you need to prove is use induction to do this proof. So if you use induction to prove a bit more general fact, which say for every closed G, the formula G in first order logic formula in Scholar form, if the model A satisfies G, then the Herbrand model H that we just construct satisfies G. You can actually prove this. And then in the proof, you can use induction on the number of universal quantification on G. Okay, so I give you 5 minutes and then you try to complete, based on this hint, try to complete the proof of this Herbrand theorem. Okay, so let me show you the here. Okay, so the proof is quite simple. So we use as indicated there, we use inductions on the number of universal quantifications in G. So if the number, the base case is this number of universal quantification in G is equal to 0. So that means G is a quantifier-free formula. Okay, so then G is quantifier-free. So now when G is quantifier-free, then we have to compare. So what we do know is that we know A satisfies G. And this is coming from assumption. Now, if we compare this interpretation, this checking whether A satisfies G, so according to this, this definition, according to the semantics, and also the process of, or the definition of our H. So this is what we have to prove. But then if you follow the inductive definition for both sides, that will proceed exactly the same. It will, if G is a conjunction, we need to check whether A satisfies the first conjunct and second conjunct. In this case, H we have to check satisfy the first conjunct, second conjunct, and so on. And then we will go all the way down to the base case, which is the predicate symbol. But for predicate symbols, we defined in the this Herbal structure such a way that for the predicate symbol, if the predicate symbol is applied to the ground term T1 up to Tk, A and H say exactly the same thing. Okay. So that we know that for all predicate symbol H and not H, P, and ground terms T1 up to Tk, say of error Tk, H satisfies P of T1 up to Tk if and only if A satisfies P T1 up to Tk. Because of the definition of H. Okay, the H is defined essentially to make this is true. And then just like said, G is closed, so it never have a free variable. So it's and then the G is quantifier free, so the interpretation will proceed just according to the semantics of propositional logic. So this case, the first case for A and the next case for H will proceed exactly the same way if you view semantics as a recursive functions. And then base case will be also exactly the same, which means that if the one on the top is true, the one below is also true. Should hold as well. So, and this is kind of perspective we're gonna take quite often. If we have a quantifier-free formula in first-order logic, then that can be understood as essentially a propositional logic formula with many propositional variables. Each of these guys, the predicate symbol applied to closed ground term T1 up to Tk, that can be understood as some unique propositional variable like a Pi in the propositional logic. And this is really saying, because we don't have any quantifications, the interpretation of G under A, interpretation of, the checking G under A, checking G under H is like checking its propositionalized versions, the propositionalized version of G under the same interpretation induced by A and H. Okay, so if we don't have a if our formula doesn't have any quantifier, that formula can be understood as a propositional logic formula. And if we have a structure in that case, the only thing matters is whether how the structure give an interpretation of predicate symbols for the closed terms in that case. Okay. So this is like, uses that kind of idea, G, because it's quantifier free, we can view it essentially as a propositional logic formula. And if we do so, all the things that matters from A to H are how they are interpreting the predicate symbol for closed term T1 up to Tk. They are exactly the same. So that's why if the A satisfies G precisely when H satisfies G. Yeah, I give a very long explanation, but hopefully this is somewhat obvious argument. The second case is now we have to do the inductive case. So here we have to deal with the quantifiers. So the first case, we don't have to deal with the quantifiers. So that's why this is very much like reasoning in propositional logic. Second case, we have to deal with the quantifier. So now let's assume that G is of the form for X, G prime. And G prime has a one less fewer variable. So then we have to check this is true. So that's what we have to check. But to checking this is the same as for A in the underlying universe of H where X is bound to A satisfies G. So this is what we have to check. That's an equivalent definition. But now we are using at this point the fact that we are having a Herbrand structure. Because H is a Herbrand structure, in this you use the underlying universe of Herbrand structure will consist of only ground terms. And so A will be a ground term. So which I will denote it as a T, to indicate it's a ground term. So then the statement that we have at this point can be simplified a little bit, because now we are saying H where X is bound to the ground term T satisfies G. So that's what we have to check. But by the translation lemma, this is exactly the same as H where H satisfies G where X is replaced by T. This is by translation lemma. So what does that mean? That means we have to, so just to bring both of them together. So now our task has becomes to show for ground terms T, H satisfies G where X is replaced by T. So this is what we have to prove. Okay. So now we are, because G where X is replaced by T, this is again closed. And also has the number of universal quantification in this case is one, the number of for all is less than the number of in this term is the number of for universal quantification in G. So we can use induction hypothesis. So we can use, it's a kind of situation where we can use induction hypothesis. And induction hypothesis say H is going to satisfy this formula if we can show that this A that we started with so if we can prove this. So then by induction hypothesis, H will satisfy G P of X, and so we are done. So then the question becomes how we can show, this property. But so this is a new goal, and this property is quite easy, because what we know, that A is gonna satisfy for all x g. So therefore, A where x is bound to A of t is gonna satisfy the g. And now, if we use a translation lemma in a most general form, the statement that we have implies G, and this replacement is true. So that's exactly what we have and what we need to show, so that we are done in the proof here. So this is quite details, but the proof is really simple. It's really saying we are using translation lemma to use from the assumptions to derive the A satisfies the G with where X is replaced by T for every ground term T. And then we use induction hypothesis and translation lemma again. So then that will give us what we need to prove for the inductive case. So that's how you can prove this theorem. Okay. Now let's go to the next. So here's a proof about this, but we already covered this. And then now, so we proved the Herbal Theorem, which say that the formula in Scholen form is satisfiable if and only if that formula has a Herbal structure. Okay. Now we want to go a bit further. Herbal structure, we want to connect it, change it a little bit further, so that we can have some statements which tells us how you can use resolutions to do the proof, to check unsatisfiability of a formula. So the one key concept that appears there is so-called Herbal expansions, which is that if I have a formula F, which is the in Scholen form, universally quantified x1 up to xn, F star is a quantified free formula. Herbal expansion is nothing but some infinite set generated from F. Typically an infinite set. So what does that say? How do we obtain this set? We obtain this set by instantiating all those universal quantification by ground terms. Okay, so replace x1 by ground term t1, x2 by t2, xn by tn for every ground terms t1 up to tn, and that's going to give us this Herbal expansion. Typically, because there are infinitely many ground terms, this Herbal expansion is going to be an infinite set, but sometimes it can be a finite set if there is only a finitely many ground terms. Okay, so then the real theorem that we're going to use to design the automatic or semi-algorithm for checking validity of first-order logic formula is this so-called ground resolution theorem. Okay. This ground resolution theorem says the following. It says that if we have a closed formula in Scholen form, so then the formula is unsatisfiable precisely when there is a propositional resolution proof of a box from this, this Herbal expansion of the formula F. So I think I should have written, so typically, I think more precise statement is this: we have a closed formula in Scholen form F, whose matrix, by matrix I mean really F star, is a CNF. It's conjunctive. I think this is perhaps make things more clear. So if we have a closed formula in Scholen form, that's a formula F, whose matrix, which means the quantifier free part, is gonna be the conjunctive normal form. In that case, this formula F is unsatisfiable if and only if there is a propositional resolution proof from the Herbal expansions of the formula F. So this is an infinite set obtained by the one as I shown there. So it's gonna be F star, substitutions, F star, another substitution, and so on. So it's gonna be an infinite set. This should be understood as a conjunction of all those formulas, okay? And because this F star is a CNF, you can think of this entire infinite set, so typically infinite set, you can think of this entire infinite set as infinitary conjunctive normal form formula. Okay? So then we can start to apply the propositional resolution proof for this infinitary conjunctive normal form formula, although what we have is a formula from the first order logic. That's because we don't have any quantifier. And when you apply this propositional resolution proof, we can just treat all these base case like a predicate variable P, or predicate symbol P applied to T1 up to Tn. We can treat this as a propositional variable Pi. Okay? So if we do so and apply the resolution proof, so that may let us conclude the infinitary conjunction is unsatisfiable. But then the theorem say that process give a sound and complete methodology to checking unsatisfiability of F. I feel like I've just said something also to make you more confused. So the formula F is unsatisfiable if and only if there is a proposition resolution proof of this. With the statement is a bit easier to understand than my explanation. Okay, so now the question becomes how to prove this. Okay. So actually this is not satisfiability, it's a validity checker. I thought I changed this. Maybe it's the next slide is written as a validity. No, not quite. Okay, so here are two exercises I want you to think about. The first exercise is to how to use these theorems to develop a semi-algorithm for checking validity for first order logic formula. Okay, so that's the first exercise I want you to do. The second exercise is to actually prove this theorem. And then to prove the theorem, as I said in the hint, you can use Herbal theorems. So that's one thing that you have to use. The second thing that you have to use is to use a compactness theorem for propositional logic. And you might wonder why it's okay to apply compactness theorem for propositional logic when we are dealing with a first order logic formula. And that is okay because of what I just told you in a few times before, which is that if you have a quantifier free and closed first order logic formulas, that can be understood as a propositional logic formula if we treat all these predicate symbol P applied to closed term T1 up to Tn. Each of them, if we treat them as a different propositional variable, like say Qi, the same P applied to T1 and Tn, they all should be replaced by the same propositional variable Qi. If you do it, then you can view this as a propositional logic formula so that you can apply the compactness theorem. So I will give you maybe 6 minutes to solve this exercise 1 and exercise 2. Okay, so let me answer this. Use mouse. Okay, so okay, so for exercise 2, suppose we are given the first order logic formula f, then we can assume, and we want to check whether it's valid or not. So here's an algorithm that I'm describing. So this is an input, and then what we want to give return is the answer to this question is going to be our output. Okay, so that's what we have to do. And then we can assume that this formula f is closed. Why is that? Because the validity of f is the same as validity of any, if we put the universally quantify any formula, any variable x inside f, validity doesn't really change. So we can assume that formula f is closed. So now what we're gonna do is the following: we negate f. So then checking f is valid is the same as negation of f is unsatisfiable. Intuitively, what validity means that it's true all the time. Negation of f is unsatisfiable means that we don't have any counterexample of f. Okay, so f is true all the time. That's exactly the same thing as f doesn't have any counterexample. So these two things say exactly the same thing. Now, to check whether this negation of f is unset, what we do is we first transform this f, negation of f, to the Scholen form, Scholemize. So that will give a formula G. Because this is Scholemizations, actually this what I say by Scholemization, it involves the transforming negation of f into rectified Prenex formula and then apply Scholemizations. But if you do both of them, this formula G is going to mean this entire process will preserve satisfiability. So if negation of f unset, then G is unset and vice versa. So the original formula is unset if and only if the G is unset. So then we have a Scholen formula G, which is unsatisfiable. Now we are and this is G is also closed. So, okay, so we do a little bit more work. So G, because it's a Scholen formula, we have a universal quantification like x1, x2 to xn, and then the G star. Now we do we transform G star into CNF form. That's exactly the transformation of any propositional logic formula into CNF form. We just applied it. We get the CNF form formula for G star. And then once you do this, then we can, okay, let me just show. Then we can apply this theorem. The theorem say, this is unset precisely when, so that's a question that we want to answer, but the theorem said to check G is unsatisfiable, all we need to do is we just need to check expansion of G, which is really in this case G star with, the Herbrand expansion of G, which is that G star where in T1 up to Tn is replacing x1 to xn, and star where different replacement and so on. We have to check whether this guy is unset. But as I said before, because now all the quantifiers are gone, and then we don't have any free variables, then this entire thing can be understood as an infinitary conjunction. So this entire set can be infinitary conjunctions. of infinitary conjunction of clauses. So we can apply, so that according to this theorem, to check whether this is unset, it suffices to just check whether from this infinitary conjunction of clauses, we can derive box using resolution. We can derive box from some subset of E of G. And in this step, so that's something that we can check. And this step can be done algorithmically. I mean, if we do this Herbal expansion, it's infinite, but it's countably infinite. So you can generate essentially an iterator, infinite loops. If you call this infinite loops, you can, in the first iteration, you generate the first instance, second iteration, second instance, and so on. So you call this iterator up to step, say, 100. Then you have a finite formula, and then you just check whether you can derive contradiction using resolution from there. If you are done, if you can derive a contradiction, then you are done. We can just say the entire original formula is unset. Otherwise, now we consider 100 plus one more instantiations, which will be a larger formula. And we again check whether we can derive contradiction using resolution theorem prover or propositional logic. And if we can find it, we are done. Otherwise, we continue. And we go on forever. And we go on, we continue. So then, this entire step will return unset. If the ground resolution theorem is true, if we return unset, precisely when, so if and only if the original formula G, is unset, which means that if and only if the formula that we started with is valid. Otherwise, so if G is not valid and F is not valid, so then in that case, this algorithm will go into infinite loop. Okay, so that's why what we have is a semi-algorithm, and actually the next lecture we're gonna show that we can't really avoid having, we can't do better than this semi-algorithm because it's checking validity for first order logic is an undecidable problem. So this is as good as we can do, in terms of computational complexity, but yeah, but this itself is actually not very impractical because some first order theorem prover uses this type of idea. So scolemmi, the first change validity into unsatisfiability, and then scolemmize, and then use a Herbal theorem and Herbal expansions. Actually, we just use this ground resolution theorems to convert the unsatisfiability checking problem into the derivability of contradiction problem using resolutions. So then we can call the resolution prover to answer that question. Now the next part is to show why this ground resolution is true. So why resolution is true. And then we use the hints that's described here. So then the hints say, now we start with the formula F that is closed and scolen form. And then we have to show that this F is unset if and only if we can derive there is a propositional resolution proof from this Herbal expansion of F. And the reasoning goes like this. So we say F is unset. So F is unset if and only if F doesn't have a Herbrand model. Okay, so that's what we have. So now it turns out this step F doesn't have a Herbrand model. Say the same thing as, by the way, F has this form and F star. This is a quantifier free. So F doesn't have a Herbrand model. It turns out to say the same thing as every some finite subset of actually that's before going this. E of expansion of F is unsatisfiable. Okay, so it turns in the expansion of F, the Herbrand expansion of F is unsatisfiable. They say the same thing as F doesn't have a Herbrand model. So it turns out they are the same thing. But now expansion of F just consists of the quantifier free, closed, first-order logic formulas. And this we can apply the compactness theorem from propositional logic. And then by the compactness theorem, this is unsatisfiable if and only if some finite subset of E of F is unset. Okay. But because our resolution theorem prover is complete, sound and complete, which means that from some finite subset of E of F, resolution can derive box. Yeah, so derive a contradiction. So this is coming from so-called soundness or correctness and completeness, which means the resolution prover can do all can prove everything with respect to the contradiction of resolution. And so both of these are really the reasoning step in propositional logic. And that was possible because we got rid of all the quantifiers, and we now end up with just dealing with closed quantifier-free formulas of first-order logic. Okay, so then the remaining step is this guy. So this is what we proved. It's a Herbrand theorem. And then, these two guys are what we already proved in the previous lectures when we talk about when we discussed about propositional logic. So what remains is this one. The formula F doesn't have a Herbrand model if and only if E of F is unsatisfiable. So we're gonna prove this. So what we're gonna prove is we're gonna prove the contrapositive about that statement, which means that F has actually we just proved this. Okay, so how you can prove, then let's prove the contrapositive. F has a Herbrand model if and only if E of F is satisfiable. Okay, so why this is the case? Now suppose we pick, so suppose that we have a Herbrand model H. So this is a Herbrand model. And suppose that this H satisfies F, but then F is of the form X1 or Xn and F star. Okay, so then this means, so some H satisfies this the formula F if and only if H where X1, Xn, Tn satisfies F star for all ground terms. So this is really coming from the semantics. I mean, in the Herbrand structure, underlying universe is the set of ground terms. So we are just binding all the values to this quantified variable x1 up to xn in the underlying universe. Then check whether this f star is going to be true. So this is really coming from the semantics. So then the next step is now we are using translation lemma. Because of the translation lemma, this thinks it say the same thing as substituted form. F star, where, I use this notation, although in the slides we use different notation, but I hope you understand what I'm talking about. X1 is replaced by T1, X2, T2, and so on for all ground terms, T1 up to Tn. But you can see this is, what you get here is nothing but the element that in the Herbrand expansion. So it's essentially say everything in the Herbrand expansion is going to be satisfied by H. But let's say the same thing as, and this is a bit informal notation, but what this notation means, every formula in Herbrand expansion is going to be satisfied H, because every formula is exactly the set of formula F star obtained by replacing X1, Xn by T1 up to Tn. Okay? So this statement shows that H satisfies F if and only if H Herbrand structure, Herbrand model satisfies F if and only if the Herbrand structure satisfies Herbrand expansion of F. Okay? So if F has a set Herbrand model, if and only if the H is satisfiable. Okay, so that's the theorem that I just proved. And yeah, so just to give a reminder about the of this theorem, the theorem say every closed formula in Scholen form is unset if and only if there is a propositional resolution proof of box from this Herbrand expansion of F. Okay, so in this lecture, what we covered is that we covered the idea of Herbrand model or Herbrand structure. And then we also covered the so-called Herbrand theorem. And then this ground resolution. And the importance is that these ground resolutions will lead to a semi-algorithm for checking validity of personal logic formula. Okay, so that's all. That's the end of this set of slides. Do you have any questions about what we discussed so far? Okay, so assuming that everybody is happy, then we're gonna move on to the next, which is about really an application of Herbrand theorem. But so in terms of this lecture 11, and it has a two big part. One is more about application of Herbrand theorem, but the other part is about undecidability of the validity question in first order logic, and actually, undecidability of validity and undecidability of satisfiability for first order logic formulas. Okay. And to talk about this undecidability, we will use the so-called PCP problem from complexity or computability theory, which is a post-correspondence problem. And I'm gonna explain what it is, and I'll also tell you how you can reduce this undecidable problem into the validity problem of first order logic, so that we can show the validity is undecidable. So there are something which is more about application of what you learned so far. There's also some part which is about some new materials more related to the computability theory, computability questions about first order logic. Okay, so this is a Herbal theorem that we studied just about like a few minutes before. But then the formula that it turns out that's quite useful is a bit kind of general version of the Herbal theorem and score-lemmaization and so on. And it turns out we can, in a sense, have a parallel version of score-lemmizations. Also, we can have a parallel version of Herbal theorem and ground resolution theorem. So here's a parallel version of this. So suppose we have a F1 up to Fn, which are rectified closed formula in Prenix form. And then we score-lemmize this F1 to G1. Score-lemmization is a mechanical process, you can do it. And then F2 to G2, Fn to Gn. But we ensured that whenever we score-lemmize F1, each of Fi, we are always using a new score-lem functions. If you have to introduce new constants, that constant is not shared by, say, G2 and G3. Each of Gi, whenever we need to introduce function symbol and constants, we're always going to introduce something fresh. If you do so, although the score-lemmization is done independently, you can show that the conjunction of F1 up to Fn is satisfiable precisely when the G1 up to Gn is satisfiable. In other words, as long as you ensure you are not using the same function and constant symbol in this parallel score-lemmization, we have this version of, we can put this parallel score-lemmization together, and that parallel score-lemmization preserve the satisfiability, preserve and reflect the satisfiability. Okay. And then the other version, which is also some parallel version of a ground resolution theorem, is this one. It says that if I have a G1 up to Gn, they are the closed formula in score-lem form, and their quantifier free part is a G1 star up to Gn star. They are in CNF. So then the conjunction of all these formula is unset precisely when if we can derive so if we can derive the contradiction using resolution theorem prover from the set of ground instances of G1 star up to Gn star. So in other words, we can, just like this parallel version of the score-lemmization theorem, this parallel version of resolution theorem said, if you put not a single formula, but a multiple formula, then nothing really changes. You can just take their quantifier free part and replace all the free variables by the ground terms. And if we derive the contradiction, derive a contradiction using resolution prover, that give a sound and complete methodology for showing the contradiction there. So the same thing as just usual ground resolution theorem prover, but you can parallelize this. So maybe the good things I want to do is think about how to prove these two things, maybe in the remaining 3 minutes. So then I will tell you about why these theorems are okay. And in the remaining maybe 3 minutes, and then we will finish after that. So you don't have to do the formal proof, but if you have some reasonable arguments, which can be kind of elaborated into a formal proof, that's enough in this. In this and maybe all the exercises that I'm asking you to do in the course. Okay, so let me explain this. Right. So for the first case, I mean, first we have to see why this theorem is say anything useful. Okay, why has the sense that what are the real contents of this theorem? The contents of the theorem is if you try to just derive this theorem from the usual collimization theorem, then we are in trouble. So the usual collimization theorem said if f1 up to fn is satisfiable, which means that we have a that satisfies f1 up to fn. Of course, that A satisfies fi because the collimization preserves the satisfiability. This is I. So what we know is that there exists AI such that AI satisfies GI. But the issue is how, for each of the G1 up to Gn, these AIs may be different. If we just use a collimization as stated, so we can't really put these AIs together to obtain something that satisfies all of G1 up to Gn. Individually, existing collimization given individual solutions or in the model that satisfies G1, potentially another model satisfies G2, yet another model satisfies Gn, but it may be that we can't really put them together. And so to actually show this theorem, we have to look at how the proof was constructed. So when we do the proof, when you obtain AI from A in the proof of the collimization theorem, actually this AI and A are very, very similar. They are almost the same, except the new is the same, except for in function or constant symbols. So it's a new function and constant symbol introduced for GI. Okay, but okay, so that's the only difference. Now, if you look at the the assumptions of this theorem, you say that each of the GI, they are using different Skolem function and Skolem constant. So that they are all, whenever we introduce new function symbols during the Skolemization, they will all gonna be different, which means that each of these AI, we can put them together. So we can construct maybe A prime by essentially, this is the informal notations, by essentially merging all these AIs. It's an informal notation. So what I meant is that for AI, underlying universe is going to be same as A, and then the interpretation of predicate symbol is going to be same as A, but its interpretation of some function or some constant symbols will be unique to AI. So we just collect all these interpretation and construct one big interpretation, A prime. So then we can show that this A prime actually continue to satisfy GI. And then because it's a single A prime, that's gonna be one that satisfies all of this. Okay, that's how you can do this. The opposite direction is the same. If you have a model, say A satisfies all of G1 up to Gn. So then the original collimization theorem said there exists some AI which satisfies Fi. But now if you remember, also if you look at the proof, the way we obtain AI from A is by forgetting the semantics or interpretation of fresh function symbols introduced during collimization. So it's real AI is a restriction of A with respect to the signature of F1 up to Fn. And then, so what that means is this AI for F1, AI for F2, and so on, they can all agree to be the same thing. Okay. So that's how you can, they are not exactly the same, but this is obtained by the restrictions. So if you take all of these AIs, and just like here, we take a union, we take an intersection of all of this, which means we just collect the common part of all these AIs that will give a model that satisfies all of this. So the key idea is here we obtain by forgetting. Here we obtain by expansions. So to construct one model, we include all these expansions to obtain the one model that satisfies all of F1 up to Fn. You forget a lot. You forget according to the A1. You also forget according to A2 and so on. You forget everything according to each of these AI. So then you get models that satisfies all of F1 up to Fn. So that's how you can prove the first theorem. Sorry, I'll give you 1 minute, then I'll finish the second. Second theorem is actually quite easy. So if one thing that you may remember is that if you have a formula like this, x f1, f2, and that's the same as for x f1 and f2. So this is something that we talked about before. I think we wrote it like this. So we can group the universal quantification together. So if we have a G1 up to Gn, which are in Scholen form, then one thing you can do is that we can use this logical equivalence. Like, I mean, there's one like this here. If x and y are different, then we can, if f1 and f2 are closed, then yeah, so we can do this f2 and f1. So we can take this quantification out. So if you just collect all the quantification in G1 and Gn using these two rules and put all of them out, then G1 star and up to Gn star is gonna be a new matrix of the new formula. And then this got reduced to the original ground resolution theorem. So you can just use the usual ground resolution theorem in this case. The first theorem, I mean, they are both parallelized version of Scholemization and ground resolution theorem. First, I have to look at the proof of original Scholemization theorem to obtain this result. Second, it's a quite easy, I mean, you can reduce very easily this parallel version into the usual version. Sorry about going over time, and that's it for today, and I hope to see you on Wednesday.